Okay, further classification. Now, there are many ways, well, there are many subtle things. Okay, so, we need to understand. So, data level parallelism is I said about gridding. No? So, yeah, I am dividing the data and you assume that the tasks are similar, okay, like grading answer books, they are similar exercise or these vector operations. Okay. So, this data level parallelism, data is our operations are similar and just we have more people to do that data. And the next is task level parallelism, where that your task for different persons are not the same. Okay, like for example, wars. So, in the eastern front of a country we have different kind of strategy. So, these are task level parallelism. So, you can't use the same program for both western front and eastern front. Okay. Google servers, they are searching, they are doing various things, they are not, your data or your query is not same sort. This is an interesting example of requirement of programming weather simulation. So, weather simulation requires not only the, well, you need the full globe. So, atmosphere, ocean, mountains, ice, pollution. So, it is possible that we can solve different components in a different servers. So, modeling ice is very different than modeling land. Okay. So, we do not have to have one program doing both. Okay. So, this is one way to, in fact, this is one people are thinking of ways to use big machine. Right now, we have machine which can do 10 power 18 operations, and that always demand is, can one program use all the machine, and if you have one of course, very powerful, but one program using all the machine is basically we do not want to do that. Okay. Matrix multiplication, a big matrix. So, why will I use a 10 power 8, I mean this big machine for one matrix inversion. Okay. So, we would like to think of problems which can use the whole machine, whether that is the important requirement. So, if I make a bigger machine, then I need somebody to be able to use that machine, a single program. So, you make a fast car, but if you do not have a driver to use the car, then this is waste, right. So, that is what is. So, there are always codes which are looked, okay, can this code run on the big machine. Okay. So, implementation of parallelism in computer. So, instruction level parallelism within CPU itself. So, we know one scheme which can do this, is called pipelining, right. So, things came, we had more hardware within a CPU and they were doing one by one, but in parallel. Well, I should not say one by one in parallel, they are fetcher, decoder, executor and writer. So, these guys came one after the other, but after some time they are all were busy. Okay. So, pipelining is able to do that job. Okay, this spectral execution. Okay, I think since I wrote it, I can tell you that if I have jumps or it needs to know where it is going to jump to. So, data is not necessarily in sequence. I have a function then, if it speculates and put that in cache before the demand, then is better for the I mean it is going to be more efficient. Vector architecture, we discussed that before. Okay. So, same operation on large data set, okay, like adding A plus B equal to C, right. So, we had lot of data coming in simultaneously. Okay. So, 16 members of A, 16 members of B, and we generate the product or sum. In graphics, we have an image which needs to be rotated. So, all the pixels have to be rotated. Okay. That is what graphics is supposed to do, and that is why it is fast. Graphics have not only 16, they work with huge data sets simultaneously. Okay. CPUs will work with 16, but graphics work with megabytes of data. Next is thread level parallelism. Okay. So, we discussed thread level, right. I mean in a computer we want to do browsing, browsing, web browsing, email reading, various stuff. So, there are different threads which will handle multitasking, thread level, they are all part of that stuff. Or this Word doc file which has to be manipulated by many people, you generate threads. And OpenMP for HPC, OpenMP is thread level, and request level parallelism is so we send a request and then it will do it, but we may have more than one request. So, ATM of a bank is request level parallelism. Okay, this server which is not, I mean data is not divided equally, there is a is basically it will execute when demand comes. Okay. Now, based on computer parallelism, so this is also important architecture kind of question, or programming, how I am going to use what program style I am using. Okay. So, SISD, single instruction stream and single data stream. So, it is coming from the program, okay, inside CPU or set of CPUs. So, this will be done in a single processor, and only thing here is instruction level parallelism, which is pipelining, is the only possibility for this. Okay. So, pipelining is the, if you recall, the data stream was also one, it gets in one after the other in a stream. Stream is basically like a queue. Okay. And processing is a CPU or some processor where the data is going to flow in. Okay. So, this is P and this is D. Now, single instruction, but many data streams. Okay. So, we have data stream is not only one data stream, but we have this data, various data streams. Okay. So, what do I do? This is called SIMD. So, I can vectorize it. No? So, my processor, if I have enough units, okay, let it come simultaneously, we will handle them all. If there is enough desk in the office, we can handle many students, so simultaneously. So, that is many data stream, but that by the way the operation is same. Single instruction stream means rotate a image. So, the same instruction for all data. If the instructions are different, then this will not work, vectorization will not work if instructions are different. Then we have multiple instruction stream, but single data stream. Now, this is a tricky thing. So, the thing which I could think of is a student is, this is a student, imagine, and is going to various desks. So, this could be DOSA desk, academic affair desk, so all that. Okay. So, these are different process, but the data is single data. Okay. This is not being used in computer architecture, but okay, in real life we can have process of this sort. And last is multiple instruction, multiple data. I told you about Earth simulator is one such example. You have different data and different instructions. Okay. So, different codes working on different data, which is basically, but we want it to do one big problem. So, weather simulation is one thing which I can think of. Okay. Google addressing many different data and using different programs, but I think this is a good example. Okay. Weather simulation. So, memory based classification we already studied, we already discussed that, shared memory and distributed memory. Okay. So, I do not want to discuss it again. This is called UMA and NUMA. So, can you fit all of it in? Well, depends on how big is the boundary. Okay. If the boundary is very big, then it is possible that P0 here, P1 here, P2 here, P3 here. So, the main programmer, main process can distribute the data to 4 process, and then each boundary can be handled by different processor and then sent back to the main program. Okay. So, depends how big it is. If it is not big, then do not do parallel programming. Okay. This sending, receiving, dividing will take time, and your code will become more complicated. So, unless your data is more than a million data points, do not do parallel programming. Okay. We will also teach you tricks which will speed up your sequential code. Your parallelization is not the necessarily is not the only way to speed up your code.